There you go. I'm recording right now. Okay, so this is the problem that we want to solve. Draw the shear moment diagram. This is a fixed support, and then you have these two triangular loads, both of them pointing downward. The first thing that you have to do is first calculate the external reactions. That's going to be common for everything. Reactions. So if we have to calculate the reaction, you can call this, let's say, A, this is B, and this is C here in between. Now, this is going to be a fixed support. 3 reactions, 2 forces and 1 moment reaction. And there's nothing else. It's just a cantilever beam. That's called a cantilever beam. What do we do? Summation of forces in Y, summation of forces in X. The first thing is these 2 triangles here. What do you think we should do here? We should break this in 2, and then you have 2 triangles, and then put a force here coming from this triangle, and coming another force here coming from that triangle, and then this distance from here to here is 2/3 of that 1.5 and meters, of course. We put here meters, and then you have this one here, which is from this part here is 1/3 of 1.5 plus 1.5, and then we solve that like that. However, this is a triangle, no matter what you do. So instead of doing that, 1 force there and 1 force there, I can just put 1 force here, because per symmetry, the resultant force from this triangle is going to be at the center. Even though it's a triangle, it's actually it's composed by 2 different triangles, this one and the other one. And the resultant of both is at the center, and you should be able to see these type of things. So then that force is going to be located there, and the area of the triangle, it will be 3 times 6 divided by 2 is 9. That's the area of that thing, 9. So if we do now summation of forces in Y equals 0, then you get that AY minus 9 minus 3 equals 0, and AY equals 12. That's the first, kilonewton. Put the units from time to time. And now we do summation of moments at A equals 0. And you do the same thing, 9 times 1.5, first the moment, MA, in this direction, positive. And then you have minus 9 times 1.5 minus 3 times 3 equals 0. And then you can solve for MA. And MA is going to be equal to 22.5 kilonewton meter. Now we have the reaction. The next step, even though it's not stated like a step, in my opinion, I would recommend you to verify that those reactions are correct. Now, how do you verify that those reactions are correct? You verify that those reactions are correct by applying summation of moments somewhere else. You can do, for example, this point here, and do summation of moments with respect to this point. Put your value of moment, put your value of AY, put all the forces, and the result should be the same. If it's not the same, then there's something wrong that you did. But I know these reactions are correct. In your case, please do not proceed without knowing if the reactions are correct. Now, the next step is finding the points of interest, as I call them, which is in reality is discontinuities. Discontinuities are those points where something changes, and those points are going to be really important because those points are going to tell me how many cuts, how many sections, How many areas should I consider when I do the shear moment diagram? That's the first thing. Those discontinuities are at the beginning of the and every point of interest, we're gonna draw a vertical line. And those are at the beginning, at the end, at the beginning, at the end. Whenever you have a concentrated force, well, right there. Whenever you have a concentrated moment, right there. Whenever you have a concentrated force, right there. This is not a concentrated force. However, wherever the distributed force begins, wherever the distributed force ends, right there, or begins the other one. So basically we can do that, and with two, and there's another discontinuity also, which is whenever you have a change in the cross-sectional area or in the type of material, but this is more for solid mechanics or mechanics of material. So after that, you put 3 lines or 2 lines horizontal, one for axial, which we don't have. I didn't do that here, right? But for summation of forces in x equals 0, ax equals 0, because there's nothing else. So now, in this case, we're gonna have 2 lines. In one of the lines, we're gonna plot the shear, and this line, this is gonna be the 0, the baseline, once again, shear in kilonewton, and then the other line here is gonna be the moment, 0, 0, kilonewton meter. Everything that plots above is gonna be positive for the shear, negative for the shear, positive for the moment, negative for the moment. And that's always the same procedure, every single time, same procedure. Okay, now, what is the next step? We have the points of interest. Now, every time that you do a shear moment diagram, I want you to do it following a point span approach. So you go to the point first, and then you analyze the span, and then the point, and then the span, and repeat, and repeat, and repeat, and repeat, and repeat. Okay. Sometimes I'm making a pause, and what I'm doing is admitting people to the conference, to the chat, because they are in the waiting room. Okay, so we'll start with the point A, and we're gonna start with the shear. At this moment, at this point, you have to ask yourself a question. Is there any concentrated shear force acting at A? You don't have to use the microphone, but you can, if you see what I'm telling you, you can just type it or say something that I remember that I'm not recording a video per se. I'm just talking to you guys. So yes, you have a concentrated force at A. What is the value for that force? And I like putting here the values for the reactions also. You find a 12, a value of 12, pointing up, pointing up. That means that the diagram is gonna jump from 0 to 12. So is there any shear concentrated at A? That's kind of the question that you ask yourself. Yes, it is. Yes. So I find this 12. That means that it's gonna jump up from 0 to 12. And that's what we did. And that's the first point over there. Now, from this point on, depends on what is the method that you're going to use for doing this analysis. Whenever you have triangles, if the triangle is like that, it's tough to use the method of the sections. If the triangle is like that, it's tougher to use the method of the sections. So I will forget about the method of the sections if I have to do something with triangles. The method of the areas, yes, I can use the method of the areas. Sometimes it's more difficult to use the method of the areas appropriately than the method of the integrals. So I'm going to do this problem following both approaches, following the method of the areas and following the method of the integrals. I know this particular problem is going to work with the method of the areas. I know it. But in order for you to know it, you have to practice a lot. I'm going to use the method of the integrals, and I'm going to verify with the method of the areas. That's what I'm going to do. So span AC, and we are gonna calculate the shear. The shear is the integral of the load plus a boundary condition over there. This C, once again, is the value of the shear read from the diagram at the beginning of this span. In other words, that C is that value over there, 12. 12. Now, this W is the equation of the load, in that span. This is the load. In other words, we have to find the equation of that triangular line or that line over there. And believe it or not, I ask you to do that in Alex, and there are some of you that still don't make the correlation between what I ask you to do and practice in math and with this. What is the equation of that line? Anybody? Well, the equation of that line is no other thing than this, like that. The equation of this line. If this is x and this is y, which in our case we call this w, but it's the same thing. If this is x and this is y, I'm looking at the equation of this line. And I have the equation of a straight line. I can use 2 points. I can use intercepts. I can use whatever. I can use slope-intercept form, which is that one. And I can calculate the slope. What is the slope of this thing? The slope of this thing is just this here, the tangent of this thing. So rise over run. Rise for this particular problem is 6 and run is 1.5. So the slope is 6 over 1.5 x. That's it. You see, now somebody put over there 9 over 1.5. 6, okay. 6 over 1.5x plus b. And what is b? B is the y-intercept. The y-intercept for this equation is 0. So plus 0. Meaning the equation of this straight line is going to be that. So w is going to be 6 over 1.5 x, or w is going to be equal to 4x. That's the equation of the load, 4x. There's nobody in the waiting room? No, there's nobody in the waiting room. Okay, good. Well, yeah, but I haven't done anything. I haven't done anything yet. Okay, I haven't talked about that. The equation of the line is that, because that's a positive slope. I haven't done anything else now. Now we have to put here our equation, 4x plus 12 dx. And now we study the direction of the loads. If the loads are pointing down like that, then I have to put a negative sign, and that negative sign affects only the integral part. Yes, of course, this 6 kilonewton is a, somebody's asking me, so you use that 6 kilonewton as your y? Yeah, of course. If you have this triangle and you imagine the points, this is the point 0, 0. This is the point 1.50. And this is the point 6, 1.5, 6. Those are the points in this triangle. Same like here. So yes, this is 6. This is the height. It's always have been the height. Okay, now we have that. Remember, this negative sign comes because the loads come down. So V equal negative 4x squared divided by 2 is just 2x squared plus 12. And this is the equation of the shear for that part. Now what do? We get and we evaluate this at where? At 0 and at 1.5. 0 is more like a verification thing. So for shear at 0, V is going to be 12 because this is 0. So this is correct. And when x equals 1.5, the shear is going to be equal to negative 2 times 1.5 squared plus 12. Negative 2 times 2.25 plus 12, 7.5, 7.5. And I have those 2 points over there, 7.5. Now, my second point is going to be here, and it's going to be 7.5. This equation is a parabola. So then we have to combine these 2 points with a parabola. And it's a frowning face parabola. But if you don't want to, and I really don't like it, using this and taking the second derivative and doing all the long procedure, I use the circle that I told you. And I say, please don't neglect infants, neglect young people instead. Positive decreasing, negative increasing, negative decreasing, positive increasing. And what is this? This area definitely is increasing because the absolute value of the function is getting bigger. But it's negative because the loads are pointing down, so it's negative increasing. It's going to be like that. And meaning this shape is going to be like this also. Somebody's asking, I thought that WX was supposed to be the area of the section. No, this is not the area of the section. B is the area. Okay, now we have that point. Let's say that we wanted to do this by the method of the areas. I'm just going to verify it, okay? Well, the method of the areas will be similar. So you go to this point, you do the first point, which you have to do the first point. And then now if you use the method of the areas, you say 12, and then you find this area here. What is that area? That area is a negative area. And this is what? This is 1.5, and this is 6. So it's going to be 12 minus 6 times 1.5 divided by 2, the area of this triangle. And 6 divided by 2, this is 9. This is 4.5, 4.5, 12 minus 4.5 is 7.5, same thing, method of the areas. And you're going to say, okay, the method of the areas is easier. Yes, I agree. I agree, it's easier. But do not forget the method of the integrals because you are going to have to use it for sure. If you have any question, keep asking questions, okay? Now, what do we do after we have this? Next step. This is not a dramatic pause, guys. I'm talking to you. What is the next step? Point C. Thank you. Point C. So now we go to the point C. Point C. This point here. Because it's point, span, point, span. Now we go to the point C. And then because this is shear, you ask, is there any concentrated shear force at C? Is there any? 9 kilonewtons down. Thank you for that, because that is wrong. 9 kilonewtons is not a real force. This is a force, and that's what I put it in red with a wiggly line, etc., etc., etc. And that's the main error that people do. That 9 kilonewton is just a result that we did. We converted the distributed load in a concentrated load only for the sake of calculating external reactions. That's why we did it. Only for the sake of calculating external reactions. That's why we did that. So the answer is no, and that means that there is no change at that point. And then we go now to the span CV. What do we do at CV? Shear is the integral of W plus C. What is C? C is the value of the shear at the beginning of CV, meaning at C, the value at that point C, read directly, read from the diagram. So we have to come here to the diagram and get that value. That's the value for C, 7.5. That's the value for that C over there, 7.5. And what is the equation of the load? Come on, anybody or everybody should tell me what is the equation for the load. I'm waiting. Negative 4x plus 7.5. Good, good. Negative 4x, wrong. Don't we need negative? I don't know. I'm asking you guys. You're giving me every single possible error that you can give me. So tell me, I only see like 6 persons out of 88 participants right now contributing somehow to this conversation. If I don't see people participating, I'm gonna just, keep the person that are here and kick everybody else out of the meeting. And I can do that. So this is a good thing about these video conferences because I have the power. Okay. I don't know why, guys, you have to struggle so much with this. I really don't. And I thought that after Alex, you would be able to do it. I haven't received the first correct answer yet. Not the single correct answer. Out of all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 people are participating, and I haven't received any correct answer yet. No, that's not the correct answer. No, that's not the correct answer either. Oh, even worse. Okay, equation of the load. Don't tell me, guys, that you don't know. Please, don't tell me that you don't know how to do this. Equation of that line. Because that's this triangle here. That's the equation of that. Oh, now we're talking. Now we're talking. The slope. What is this value? We already say that. That value is 6. What is this value? This value is this one, 1.5. What is the equation of the load? Y equals mx plus b. What is the slope? Rise over run. 6 over 1.5, only the negative because this is a negative slope. So y equals negative 6 divided by 1.5 is 4. 4x plus b. What is b? B is the y-intercept. This value here, 6. And that is the equation of that line. And this is not a dramatic pause. This is just to show you that you guys have the knowledge. You guys have the previous knowledge to do this. And you just don't care. You forget about that. And you don't want to put it there. Now, this is the equation of that. Now, I had to put that inside that equation. So V is going to be the integral of this plus C, which is 7.5. However, these loads are also pointing down. If these loads are pointing down, that means that I need a negative sign here in front of that, and that will be my equation for the shear. Now I just have to do the integration. Let me mute this phone because I don't know who is calling me. Okay. And we do the integral of that. So the shear when I do this integration, negative times negative is gonna be positive. So 4x is gonna be 2x squared because it's gonna be 4x squared divided by 2, negative times negative. Minus times positive is gonna be minus, and this is gonna be 6x. And this is outside, so this negative doesn't affect that, and it's outside the integral, so plus 7.5. That should be the value for that, if I'm not mistaken, which I could be, but let's check what happened. So now we come here and we said at 0, V at 0, because now we have to start again from 0 to 1.5. So at 0, this is 0, this is 0, 7.5, which coincides with my value here, means we might be correct. And then the other point is at 1.5, at 1.5. How much, don't calculate anything. How much do you think should be the value when I put here 1.5 without calculating anything? Quick. 0, 3, 0, 3, 0, 3, 0, 3, 0. Oh, we're half and half. 0, 0, 3. It should be 3. Why 3? Because this, when I go to this point, I'm gonna find this force of 3, pushing it down to 0. Okay? Now, let's see if it's 3 or not. 2 times 1.5 squared minus 6 times 1.5 plus 7.5. This is 2 times 2.25, so that means that is 4.5, and this is 4.5. 2.25, this is gonna be 9, 7.5, 3. There you go, 3. Now we come here and we say, oh, this point here is gonna be 3. Right there, 3. And now we have to join these 2 points with the parabola, and this is the parabola, as you know, right? And what is a parabola? You can use whatever method you use, but honestly, please don't neglect infants. I neglect dumb people instead. So if I do that, this is gonna be positive or negative? Negative. It's gonna be negative because the arrows are pointing down. And the absolute value of the function is getting smaller, or the y, if you want to, is getting smaller as I move from left to right. So this is gonna be negative decreasing. And negative decreasing is this, meaning these 2 points are gonna be joined like that. And now we go to the, and I'm gonna check this by areas also. But then I wanna finish this. I go to the point B, and if I go to the point B, I get a 3 from my diagram, and I find this 3 negative, which means 0, and then you can say your well-deserved yes over there. If we know that it will be face open parabola based on the equation, why do we need to use that chart? You don't. You do whatever you want to do, whatever pleases you. Now, if you know that it's a cubic equation, then I don't know if you want to use the chart or not. Because when we do the integration of these, it's a different story. Okay, anyway, let's try this by areas, this part, because I told you I was gonna do it by both. So if we try this by areas, I come here at the point C, and I had a value, previous value of 7.5. And then I find this area, which is also a negative area, this area. And this is 1.5, and this is 6. So this is gonna be 7.5 minus 6 times 1.5 divided by 2. So this is 7.5 minus 3, 4.5, and this is 3. And then we go to that point. And now I'm gonna give the question back to you. I'm gonna return the question back to you. You say, if we know that it will be face down parabola based on the equation, why do we need to use that chart? Now I'm gonna tell you, if you're doing it by areas, do you have the equation? Okay, I rest my case. You don't have the equation, then you need to use the chart, or you need to come with something else. Is it still working, the video? Can you still see the video working? Because it says something about here of internet is unstable or something. Okay, good. Now let's go to the moment diagram. And the moment diagram is just a repetition of what we did before. I come to the point, first thing, point A. That's the first thing that we do. We go to the point A. And we ask ourselves, is there any concentrated moment acting at point A? And the answer is yes. When I go to the point A, I find this moment, which is a moment reaction acting in this way. And you can say, oh, I'm gonna do clockwise or counterclockwise, positive or negative, or whatever convention you want to. I like to do this. You don't have to. And I said, okay, if I complete this circle, I see the arrow in this side, and the arrow is pushing it down. That means that here, I'm gonna have also a jump down in the diagram. And this value is 22.5. That means that I'm gonna start with a negative value of 22.5 because it's pushing from 0 to that. Remember, this is positive, this is positive. And we start like that. And that's gonna be the same thing no matter what we do, no matter what method we use. You always start like that. If we're using the method of the integrals, then I have to say that the moment is the integral of the shear plus C. Now, in this case, C, and this is extremely important, and this is extremely important because this is what is providing you that C. C is the value of the moment at the beginning of the span AC, meaning at A, read from the diagram. So that C is going to be negative 22.5. And this V, we got it before. We got that V here. This is the value of V, equation of V. So this is what we are integrating. That value, negative 12 plus, which is minus 22.5 dx. You do not put any other negative sign here because then you will be doing double negatives. And this is not the idea. The negative sign on the direction is already integrated when you did the shear, and that's affecting also the moment. So when we do this, the moment is going to be equal to negative 2/3 x to the third plus 12x minus 22.5. If we do the moment when x equals 0, why 0? Because at the beginning of the interval, x is 0, and at the end of the interval, x is 1.5. This is 0, 0, negative 22.5, which is the value that we started with. Kind of makes sense, right? And if we do now moment at 1.5, the moment at 1.5 is going to be equal to negative 2/3 of 1.5 cubed plus 12 times 1.5 minus 22.5. Calculator. I'll be back. This is negative 2/3 times 1.5 to the third plus 18 minus 22.5. That's negative 6.75. Negative 6.75. That means that I need to plot that value. Now, if I have this equation, how do I know the shape of this? Because this is not a parabola, this is not a frowning face or a happy face. Then you have to either use your calculator that plot it for you or do something else, I don't know what, and take the inflection points and take the second derivative, or don't neglect infants. Neglect on people instead. And then you come here and you study this shape. Positive first because it's plotted above. Now, the values, as you can see, of the absolute value of the function is getting reduced as you move from left to right. So that's positive decreasing, and positive decreasing is this. Now, I'm gonna use some people results, some people comments. Somebody said positive increasing. Now, look at the if it's positive increasing, I mean that could even be joined here by that. But let's say that by any chance you get negative increasing or negative decreasing and you get confused. If this is negative decreasing, the shape would be this, right? There's no way that you can join these 2 points with this shape. I mean, if you think about that, you say, oh, this is gonna be negative decreasing. I don't know for what reason, for whatever reason. This is impossible that this line will join these 2 points. If you say negative, if you say, I don't know, negative increasing is this. There's no way that I can join these 2 points with that because that will come down like that. Positive decreasing, positive increasing, yes, both of them could join. But remember the absolute value of the function is decreasing when you move from left to right. So it's positive decreasing, and positive decreasing is that one. Now the next step is, I'm sorry, areas. How do you do that by areas? Can you do that by areas? 2/3 BH. I don't know what 2/3 BH. That's what you will do, 2/3 BH. If you do 2/3 BH, it's wrong because this is not 2/3 BH. But you're right, but you're wrong. What you have there, if you're gonna use areas, what you have there is this. That's what you have there. And this is, okay, now you completed it. And this is 1.5. So basically what you have is this rectangle and this parabola. But be careful because you cannot do this for every shape. In this case, you can. You're using the whole triangle. And it's a triangle. So this is a parabola. What is this area? This area is 1.5 times 7.5. That's that area. And the parabola, and this is B and this is H. This portion is 2/3 of B times H. And this portion here is 1/3 of B times H. That's the way you calculate the parabola. So in our case, the area of this is going to be 2/3 of 1.5 because it's the fat part, this part, the fat part. 2/3 of B, 1.5 times H, but H is not 12. H is 12 minus 7.5. This is 7.5, this is 12, this is 12 minus 7.5. Plus the area of the rectangle. And this area, the total area there, will be, this is 1, this is 5, 1.5 times 7.5, 11.5 plus 5, 16.25. 16.25. I mean, this is 16.25, the area. And this is a positive, where's my drawing here? We started with negative 22.5, and we added this area, 16.25. This is not 675. I'm doing something wrong here, probably, like usual. Yeah, here. I said this is 5. This is not 5. This is 4.5. This is 4.5. 4.5 plus, where were you guys that you don't correct me? 15.75. 15.75 as the value. And minus 22.5, 6.75. And that's the value that we got before, negative 6.75. This is the value that we got right there, negative 6.75. Any question? Are you still here? I'm talking to myself. Okay, good. No, you're not here. Okay. Bruno, you're not here. Okay, anyway. So now we have this point. Keep going. What is the next step? Now we go to the point. And we say point. This problem, I'm taking my sweet time with it, but you can really do that fast by using the method of the areas. So now you go to the point C. Point C, this is page number what, 4. So point C. Now if we go to the point C, you can say no concentrated moment because I don't have any concentrated moment at point C. No change. And then we go to the span CB. Span CB. Okay. What should be the moment when I do my equation and I put here my moment? How much should be that moment? When I calculate this, whatever, the moment, once I reach this point, how much is that? Are you sure it's 0? Well, if you know it's 0 because you have to close in 0 and you don't have any concentrated moment, not 22.5, 0. You know this is gonna be 0 when I close here. And you know, once again, please don't neglect infants, neglect young people. Instead, I can cheat, but I can cheat with knowledge because I know this is gonna end in 0. And I know this is positive, and I know this is decreasing. So positive decreasing is this. I can complete my diagram by saying this. I'm saying, yes. And it's done. However, your professor is going to ask you to demonstrate that, not just to tell me that. So then we have to do it. But you know, you can finish it like that. And I know it's going to be good. Now let's do what I have to do. The moment is the integral of the shear plus C. This value C is the value read from the diagram at the beginning of the interval. So that means that is negative 6.75. And the equation of the shear, we got it before here. That's the equation for the shear when we did it before. So moment is going to be the integral of this minus 6.75. This is 6.75. And then we solve this. Negative 2/3 of x to the third minus 6x squared divided by 2, 3x squared plus 7.5x minus 6.75. So for moment at 0, this is going to be negative 6.75. And for moment at this length, 1.5, this is going to be 2/3 of 1.5 to the third minus 3 times 1.5 squared plus 7.5 times 1.5 minus 6.75. And if this is not 0, please lie to me and tell me that this is 0. But I don't believe you anyway, so I'm going to do it again. Yes, thank you, Lord. 0. And then now you can say this. No, let me just emphasize that. Now you can say that. Okay, good. Now, if I use the method of the areas, let's see if the method of the areas work for this part. Coronavirus. So let's do the method of the areas. Now I have this value here. This value, I'm sorry, negative 6.75. and I find this area. And that area is this. This is 3, this is 1.5, and this is 7.5. 7.5. Now, if we calculate this area, once again, this is going to be a rectangle, and this is going to be the other portion of the parabola. Remember, if you do this portion, it's 1/3 of b times h, and this is the skinny part of the parabola. So then this is going to be 1/3 of b, which is 1.5, times h. H is this, 7.5 minus 3, plus this area, 1.5 times 3. And this is equal to 6.75 minus 6.75. And then you have negative 6.75 plus 6.75, 0. Negative times this, 0. And then we can do it by areas. Yeah, taking the integral, the definite integral of the parabola is the area, definitely. And then we finish, and then we finish. What about it? You like it? Lie to me. Say yes, I like it. Oh, okay. So you're lying to me then. Okay. If you don't like it, it's because you're lying to me.